Oh, by the way, just make sure that welcome back to CE 528 recording. I did post all the lectures and all the discussions that we've had so far in the class online on the YouTube playlist for this class. So I hope you all are checking it out if you need to, if you missed something. So that opportunity is always there. And also it was great to see some of you in the ITE meeting this afternoon, or this morning / afternoon. So I hope you're all able to make there. If you didn't, please make to the next meeting, because there won't be just professors talking, but next meeting will have actual professionals who work in the field. So, all right. So I want to get started on production theory and how that gets applied to the transportation system. How do we think about this? And this will get somewhat challenging, and the homework problem that I have on this is also somewhat challenging. Again, it's not, I haven't assigned that homework, but once we finish this lecture, I will assign it. And that is only one homework problem, but it is somewhat challenging. So I hope you guys are going to pay attention to this lecture. It comes from economics mostly, and the production theory comes from economics mostly. And they do cover that in industrial engineering as well. So let's think about transportation system as a production process. It's input of resources like time, equipment, fuel, and then output of services. So you have the system that takes the inputs and then provides the outputs of services to the system users. Oh, are you guys not seeing the PowerPoint? Okay. Thank you for letting me know that you're not seeing the PowerPoint. Give me 1 second here. Okay, very well. Can you guys see the PowerPoint now? Give me a little thumbs up. Okay, perfect. Thank you. Okay, so this is just one representation of how you think about the transportation system as a production process. You have the input of resources, you have the transportation system, and that provides the output of services. And the output of services could be ton kilometers if you're talking about the freight, passenger kilometers, passenger miles. It could be number of passengers served, number of trips provided, whole host of things. And it takes time, equipment, fuel, all those other labor, all those other inputs there. So in this slide, I outlined two basic problems that are associated with this viewpoint. They're not as much as problems per se. What they are how thinking about production theory in the context of transportation systems, how is that different from how maybe a manufacturer looks at, how a manufacturer looks at that process. Because if you're talking about the manufacturing process, all the inputs are provided by the same single entity. But that's not the case with the transportation system. For example, the truck fleet operators are independent of the agencies that may make decisions about the roads, about the tolls. And then travel time of bus passengers are consumed resource, but they're not necessarily felt by the bus operators directly. But if you think of the manufacturing process from the point of view of manufacturing companies, all the costs are borne by one single entity. Obviously, there could be negative externalities related to pollution and so forth. But in terms of like the production cost that is felt by, so all is borne out by one agency. There are no two things that bear the cost of that, And then system outputs are also quite multidimensional. So when you're producing widgets at a company, you just have to count number of cars, or number of widgets, number of whatever you produced. But Transportation system outputs, on the other hand, they're different. 1 ton-kilometer of transport in which 20% of the goods are damaged is not the same as ton-kilometer of transport in which less than 1% of goods are damaged, right? They're obviously two different things, right? So 1 ton-kilometer of transport, one widget is same as the another widget. Or one car is the same as another car. But if you think about it in the transportation system, 1 ton-kilometer may not be the same as another ton-kilometer. And so you have to think about those things as well. Production function, the definition of the production function, it's a mathematical relationship between output obtained by a family of production processes and all efficient combinations of the resource input. And I'm gonna talk about this efficient combination in just a second, okay? So I'll talk about this efficient combination, what that actually means. So that's not a trivial thing. That's not something that I just threw it in there. It means something very specific in the production theory. So we'll talk about that. But the idea is that how all the inputs get combined through the production process to produce an output. You are basically, when you do that, that's when you're representing the production process as a production function. Okay? So what do we mean by efficient combinations? So that's what we're going to soon see next. So let's think about this. Very simple example, but I think it clarifies that in the context of transportation. But again, you will notice that the output that I'm using, it's still very traditional production theory-like. So I hope you'll pick up on that when I talk about this. So let's say there are 3 different technologies that you can use to build 2-lane rural highways. 3 different technologies are different. When I say technologies, they essentially rely on 3 different combinations of labor and capital. 3 different combinations of labor and capital. Labor will be worker days per day. So let's say, and this unit might sound strange to you, but what it means is that, let's say if you hire 5 workers every day. So basically 5 workers working one day, it's basically 5 workers. And then per day is essentially that. And then capital, which is the capital equipment here. And let's say that's bulldozer days per day. So maybe you rent 2 bulldozers for the whole day, or 5 bulldozers for the whole day. And now you can utilize number of bulldozers, a different combination of number of bulldozers and number of laborers, and get different outputs of 2-lane rural highway completed. And that output will be measured in terms of kilometers per day. So let me show that demonstration. Let me demonstrate that process using graphs. So you could see that I have here 3 different technologies, A, B, and C. And in all of those cases, in these straight lines here that I'm showing you, you're probably seeing on the screen, these 3 straight lines, they demonstrate as you add more inputs, how much more highways can you produce. Obviously, as you move to the top right of this chart, you can produce more highways because you're employing more workers on the x-axis and more bulldozer on the y-axis. So as you move to the top right, further along each of these production technology curves, you're able to produce more highways. Now, if you want to build half a kilometer of highway, using technology A, because remember this curve lies for technology A. If you want to produce half a kilometer of highway, you'll probably hire, it looks like to me, 3 workers and 1 bulldozer. So if you bring in 3 workers and 1 bulldozer for the whole day, you will be able to build half a kilometer of highway using technology A. And then obviously I'm just interpolating the numbers here. And if you want to build half a kilometer of highway using technology B, you'd probably need to rent the bulldozer for a third of a day. So maybe for about 3 hours, you are going to rent the bulldozers. If it's a 9-hour work day, let's go with that. And then you can bring in 10 workers. So if you bring in 10 workers and rent the bulldozer for about a third of the day, and again, I'm interpolating here. So assuming this is about a third of a day here, you're also able to build half a kilometer of highway. Okay. And that's basically, and if you move along and hire more worker or get more bulldozers, you can build more and more highway using technology A and technology B. And then somewhere in between, there lies a technology C as well. Right? Now the question is, let's assume the technology C is not there. Okay. So I'm going to, for a second, I'm going to assume that technology C is not there. Okay. So let's assume that this wasn't there. If this wasn't there, think about the line, the dashed line that joins the curve for technology A and the curve for technology B. Okay. So I'm assuming that technology C is not there, right? Think about that. So the dashed line that joins A and B, let's say for a second, in the absence of line C, it represents the pathway only in the presence of technology A and B, that represents the pathway or the locus of the points that can help you produce 1.5 kilometers of road. And then I'm going to draw another line here. And then the new red line that I've drawn, and maybe I should draw it with a different color here. Give me 1 second. Draw a green line and a purple line. So these green and purple lines that I'm drawing right now, they represent the pathway to build half a kilometer of road, or the locus of points that can help you build half a kilometer of road. And then the purple line represents 1 kilometer, and then the dashed line that represents 1 kilometer. And then the blue line you could have that can help you build 2 kilometers of road. Right? Now, and I'm assuming the C is not there. So those lines, the green, purple, dashed, and blue line, they represent the efficient combination if C weren't there. If C weren't there, this technology C wasn't there, that represents the way to generate 1.5 kilometer of roadway. Okay, how should you combine labor and capital together, labors and bulldozers together to build that amount of roadway per day? Now let's say suddenly you can't come down with technology C. Now you come up with technology C is in the market suddenly. And that represents a different way of building the roadway. It's a different combination, still requires labor and bulldozer. But let's say they have perfected a system. Maybe they have something ongoing there that can help them, that can help the road builders. Maybe it gives them some better instructions on how to do things. in technology C. Or maybe they give some feedback to the workers if they're doing something right or if they're doing something wrong. The workers get feedback. Whatever that innovation is. But let's say somebody came up with technology C to build roadways. Now the question is, would you still want to be on the path, the green, the purple, the blue, and the broken line path that connects technology A and B? Would you still want to build half a kilometer, 1 kilometer, 1.5 kilometer, or 2 kilometers of road per day using those combinations of A and B? Would you still want to build? So if your goal was to build 2 kilometers of road, would you still want to be on that blue line is the question. Would you still want to be on this blue line right here to build 2 kilometers of road? Does it still make sense to build 2 kilometer road per day using blue path or blue locus? Please type up in the chat. Yeah, right? You can build for a smaller combination of labor and capital 2 kilometers of road with technology C. Okay, so now your efficient combinations do not go through just A and B. Now your efficient combinations go through these different paths. Oops. Okay, so for one mile, for 1.5 miles, and for 2 miles, you're now able to come up with paths or better combinations or more efficient combinations that can generate same amount of roadway for you, or that can build same amount of roadway for you. Yep, that's right. Blue line is not, the original blue line was not as efficient as path C. So now your new efficient combinations are going to go through. You can match A and C, and that will represent the best way to build 2 kilometers of road. And then you can match B and C also. So the most efficient combinations will now look like what I show. To build 1.5 kilometer of roadway, we'll go through these points. Okay. And these lines that I'm showing you, in the absence of A, C, or in the presence of C, these are what we call isoquants. Isoquants means combinations of labor and capital that produce the same amount of output. Isoquants, same quantity. Okay. So these broken lines that I'm showing you are the isoquants. Questions about this? If something's not clear, please let me know. I'll give you 30 seconds or so. I'll pause the recording even. So the question that I've been asked is, what does this green line represent in this chart? Okay. What is that representing? Okay, so that represents, let me just type that up here. So green line, efficient combination, produce 0.5 kilometer per day. Okay, so green line is the efficient combination. Under what condition though? The original green line is the efficient combination to produce 0.5 kilometer of roadway, but under what condition? Any thoughts? See something in the chat? Let me quickly check it. Yeah, when only A and B technologies exist. So in the absence of technology C. Because green line connects the 0.5 kilometers. So green line and the purple line and the dashed line and the blue line that I drew They're basically isoquants, efficient combination to produce same amount of roadway every day in the absence of technology C. Does that answer your question? Please let me know.
Yeah, kind of. What I was wondering was, would that mean that that combination is the 10 worker days and then 1 bulldozer day?
That's right. So 10, no, not quite. No. So, sorry. Yeah. So no, it would mean that 10 workers and about maybe 1/3 of bulldozer per day. So you bring in the bulldozer for some hours and you employ 10 workers for the whole day, or you bring in 1 bulldozer for the whole day and maybe employ 3 workers.
Okay, so
they produce the same amount of roadway.
Okay, thank you.
Yeah. So what I'm trying to tell you is that you can also tell by looking at these graphs, the way that they are plotted, you can see the the technology A is more capital heavy. It requires more capital. And technology B is more labor heavy. So, and then that could also provide some context, is like, if you're less industrially advanced society, maybe you rely on more labor heavy technologies, versus if you're more capital heavy society, then you rely on more technology A, for example. Okay. All right, thank you for that question. Please, any other questions? Okay, so I'm going to go and go on to the next slide. Right. So when you make that efficient combination of available function, production processes, that defines what we call the production function. It is possible to combine processes A and B to create output with any mix of input, but these combinations are inefficient in the presence of production process or the technology C. Okay? So that's what we talked about in the last slide. And then this is the efficient combinations. And then this is what we call the isoquants, efficient combinations of input that produce the same levels of output. And I got the worker days per day. I got the bulldozer days per day. Make sense? Questions? Since most analytical techniques look at variation of inputs considered one by one, so when we're talking about production process, most of the time we are interested in, moving gradually in our resources. So for example, the funding gradually increases, for example, and then you learn, hey, maybe I can hire one more product or one more laborer or one more bulldozer. How much extra road can I produce? So marginal product is examined by holding all but one input constant. So you change, I'm going to hold my labor at constant. How much extra road can I produce if I can get one more bulldozer, for example? Or you could say, how much more I can get by adding more labor, for example. So you can think about that marginal product graph by drawing a horizontal line at 1 bulldozer per day. So you keep the bulldozer at 1, and then you figure out if you are at, maybe this is like 2 workers versus when you are at maybe 11 workers. And when you are at maybe 23 workers, and I'm just sort of, and 40 workers. Okay, with 1 bulldozer and 40 workers, you can produce 2 kilometers of road. With 1 bulldozer and maybe 23 workers, you can only produce 1.5 kilometers. And 1 bulldozer and maybe about 12 workers, you can produce 1 kilometer of road, and so on and so forth. And then you can decide which isoquant you want to operate on if you can get hold of one bulldozer only per day. Okay, and that's what the marginal product idea is. And then you could do the same thing. If you were to draw a line, you could do the same thing at 2. I know I'm not quite there yet, but you could do the same thing at 2. You do the same thing at 3. Do the same thing at 4. Whatever. Right? So you could have those combinations if you are able to get. So just, and then you could do, there's no reason why you couldn't do it for the workers too, right? You could fix, okay, I'm only going to be able to hire 10 workers or 20 workers or 30 workers. You just fix one of your inputs and then just figure out how much more road you could build. So to build 1.5 kilometers with 20 workers, you probably need to get the bulldozer for 3/4 of a day. But then you'll have to build the roads of 2 kilometers. You'll probably have to keep the bulldozer for 1.5 days. So you have to get one bulldozer for the full day and another bulldozer for half the day. Things like that. And then you could get your marginal product going. Is everybody clear on the idea of the marginal product? The idea of marginal is how much more do you need to produce that extra kilometer of road? Or how much extra road could you produce if you add one more unit of input? Questions? Move on to the next one. Okay, now this is what, if you fixed your bulldozer number at that one number that I showed you in the previous slide, if you basically cut a slice here, and then you just plotted workers and number of road, amount of road produced. So now the one thing that you might want to note here is that my axis labels have changed now. My X is still worker days per day, but my Y axis now is kilometers of highway built using one bulldozer. That using one bulldozer is what you get from having that one bulldozer at fixed value. And then now you're just plotting those to workers and number of kilometers of road built. Now I'm showing you here two things, APP and MPP. APP represents average product produced, and MPP represents marginal product produced. Can you, by just looking at the graph, and I'll probably get rid of this annotation here. Just by looking at the graph, and you will notice that this is doing it at the same point here on this curve. On the curve, they're talking about the same point where you're using 5 workers. Just by looking at the graph, can you conceptualize? And you could say average physical product. If it's a physical product, you could say average physical product or marginal physical product. That's another acronym that's sometimes used, but you could have average product produced versus marginal product produced as well. But let's think about the definition of APP and MPP in the context of that point that I'm highlighting in red on the curve. Can you write out the definition? What does APP stand for and what does MPP stand for? I'm going to go ahead and pause the recording, let you think about it a little. I'm going to go ahead and I'm starting to record again. So marginal physical product or the marginal product produced is the slope of the line at that point. That's MPP. Gives you the rate of change. That means if you add additional worker at this point, how much extra road could you produce? We are very interested in that usually. Average physical product or average product produced is just the slope of the line from the origin to that point. So just basically y divided by x. So you can easily get the slope of that line using this. Using the rise over run from that point. It's the slope of this line right here. That's it. That's what that is. Average physical product. And we are interested in sometimes when we are doing average cost calculation. And so does that make sense? Any questions about this? No questions? Okay, so I'm assuming that's pretty clear, because now you tell me, why is this point so special? What's so special about this point right here? If you understand the idea of the marginal product, you should be able to tell me what's so special about this point. Any thoughts? Pause it for a second, think about it. What I heard from Dana here is that as you progress along the curve and keep measuring the slope of different tangents along this curve, you'll notice that the curve becomes steeper and steeper. That means marginal returns keep increasing as you move forward. As you build more and more roads by hiring more and more workers, your slope keeps going up and up and up. But beyond this point, the slope becomes maximum. And after that point, the slope starts to go down. The line starts to become flatter after that. So we're also very interested in that particular point in our production processes, because we want to know up until what point it's sufficient to add more workers or add more resources to build more road, and at what point the marginal returns start to decrease. You don't get as much extra road as you were getting before by adding more workers. You might still have to add them because you might have to have some deadlines where you have to finish the project and whatnot. But you still are very interested in that point. Make sense? It's a very important point as to when the marginal returns keep increasing versus when they start decreasing. Questions about this? No questions? I'm going to move on. It's the marginal physical product. At a given level of output, this is the additional amount of our product produced by one more unit of resources, dz over dx1. Average product is, for the given level of output, ratio for output for a particular point, z over x1. And you can also think of that as the slope of the line joining that point to the origin. Increasing marginal returns, you have the upward sloping marginal product function, increasing average product. And then you have the downward sloping marginal product function, where you have decreasing average product as you provide more inputs. Okay? So all these concepts we just talked about just in the words form. I hope all these definitions make sense. Any questions about those? There are some other aspects to the marginal returns, and those are indivisibility. You might not be able to hire, like, some companies might require you to rent the bulldozer for a full day or not at all, right? They might not give you bulldozer for a few hours. So that could become a consideration, that either you can get one bulldozer or two bulldozers, not like a fraction of time. And then we're usually interested in the portion of production functions which have decreasing return, decreasing average product. You want to find out where that happens. Because if output increases faster than the resources used, so if you're on that left side of the curve, you always might want to increase output. Assuming constant prices, and it's not like when you use two bulldozers, they charge you more for it. And then calculations might change. But other than that, if you're operating on the left side of this curve in this portion, you want to keep increasing the output up until at least this point. Let's think about the economy of scale. So I'm going to make a very simplified model of the economy of scale here. Think about a cargo ship modeled as a cubic box of dimension S. So obviously cargo ship is much more complicated. You need the crew, you need the stuff to go in and out, you need the crew for that. And you need technology for propulsion technology, whatnot. You need a lot of things. But think about cargo ship for a minute, because it's very clarifying, as a cubic box of dimension S. You have the length, width, and height, S. If you double the S, you increase the surface area, and surface area obviously of a cube is 6 times S squared, because there are 6 surfaces, each have an individual area of S squared. You add them up, you get the surface area to be 6S squared. Now let's say you double that dimension. Your construction material requirement only goes up by a factor of 4, because all you're doing is you're increasing the surface area by a factor of 4, because 6 times 2 times S squared, which is 4S squared. So now the area is 24S squared. So it has gone up. Your construction material requirement has only gone up by a factor of 4. What about your volume capacity? Because remember, the volume is S cubed. You double the dimension, it's the volume. The new volume is going to be 2S raised to power 3, or 2S cubed. So now your volume has gone up by a factor of 2 times 2 times 2, 2 raised to power 3, which is 8. What does that mean? What does that tell you? That means your productive capacity increases roughly twice the rate of required material to build the ship. And that explains why cargo ships are usually large, very large cargo ships. Right? Because they have an increasing marginal return. Now, why they are not like even more large, you might ask? Because obviously, if you make them too large, they get stuck. Remember what happened earlier this year? What happened? Do you guys recall what happened? What I'm referring to here? In terms of large vessels, do you remember a news story from maybe 6 months ago? If my concept of time is correct. Let's see if somebody remembers here. Yep, yeah, the ship that got stuck in Suez Canal. Yep, not Panama, but Suez. In Suez Canal near Egypt. Yep, that's right. That's exactly what happened. So obviously you have limitations on how large you can make the ship. But if you just kind of think about this economy of scale, that explains why potentially the cargo ships are so large. Obviously, you cannot make them increasingly large, but because, and then obviously if you have too large of a ship, loading and unloading costs going in and out might increase and whatnot. And local demand for cargo transport is limited, and timely delivery of goods is important. It's not like you just want to fill them up and move it. You have to actually get them somewhere too. But you can see how the economy of scale sort of comes into play. To make cargo ship large, obviously they cannot be unlimited size, obviously, because of all these factors that I'm talking about. But they're fairly large because there is that economy of scale to be achieved by adding, where material requirement only goes up by a factor of 4, but your carrying capacity goes up by a factor of double that, right? And that's the idea of economy of scale. Stability of production function over time. A normal production function is based on the assumption of fixed technology and fixed quality of inputs. In reality, technologies obviously change over time, and some of the inputs become more productive over time. So, and that happens all the time, especially if you're a developing economy in the first half of 20th century. So that's basically last century. 100 years ago at this time, the productivity of inputs in the US, labor and capital, was growing by 1.5% per year. That's a pretty big increase in productivity. So when you're a developing country, you have that productivity increase quite a bit. About 40% of that increase was due to improved quality in the workforce. 60% was due to better equipment. That's just some estimate that has been made by some studies. So that's why if you're using production functions, you must include productivity growth if you want to have your models to be useful for the long term. Especially countries like China and India and Brazil that might still be growing very rapidly or somewhat rapidly. That is indeed the case. You cannot use a constant sort of, unless you're talking very, very short term, the production functions have to account for that productivity increase. Now let's think about the cost concepts, okay? The most important idea in production theory is the linkage between transportation outputs and consumption of resources, right? Now, all these resources that we talked about, labor and capital, when we were building the road, for example, that 2-lane highway that we were building, we had labor and capital. See, labor and corporate capital also have their relative costs, right? So you can convert those numbers of the dollar and the bulldozer that you were renting and whatnot into dollar amounts. Right? So you can define the cost as the decrease in wealth which results from committing a resource to a particular use. So when you hire laborers, you pay them. And when you rent the bulldozer, you pay that company. Now, in developed economies, you can always just convert them. If you have stable prices, you can just convert everything into a dollar amount, and that works most of the time. But sometimes that might not be the case. In some economies, that might not be the case, and the nature of cost might be different. So think about this, and I see this idea sort of, and let's see if you heard of that news story. Let me explain this concept here in this slide, and then maybe we can potentially talk about one of the things that was recently in the news. Assume that you're in charge of a large construction project in an isolated location. You hire 1,000 workers that were maybe doing some sustenance agriculture. They weren't really employed. You pay the workers $10 per day per worker, but then you've also built the housing and markets. Sort of very, and then the workers have to spend like $9.50 per day for food and shelter. But if you think about it, the housing and markets actually cost you, the person who is building in charge of that construction project, only costs you $4.50 per day. So on this project, your daily cost of worker is not $10, right? It's not $10 at all, because you get that $9.50 back. And then, right? So you're only spending 50 cents to give to the workers, and then providing housing and market costs you $4.50. So it only costs you $5 per day, even though nominally you're paying 10 workers $10. And there was in this news about, I think it was Amazon, where they were going to create Amazon cities, and this was sort of the idea. So sounds somewhat dystopian to me. So, but that does happen to be reality in some isolated locations, especially in developing economies. Sometimes these kinds of things happen where many resources are underutilized. So if you have a labor that's underutilized, there's a lot more labor available to you, and then that resource could potentially be exploited in this way. So the cost concept might be different, and you don't sort of have that type of example. Mostly that type of example in the US, in the developed economies. So you can convert directly the cost that you pay the workers into dollar amounts and work with that. But I just want you to be aware of that. That's not the cost concept. The nominal concept of cost is not always the real estimate of the cost when you're dealing with things like that. So that's one idea of the cost concepts that you have to be aware of. That your real cost might not be, your nominal cost might not be a real cost, because you might be recouping some of the money that you're paying to the worker, but that doesn't quite jive with what you might see here in the US context. The other significant cost concept is who pays? Who bears the cost? Cost of construction and operation of transportation ways, roadways, airways, waterways are typically borne by public agencies. The DOT, the US DOT, the airport authority, waterways, they're all borne by agencies, public agencies. There's a major exception to that in the US though, Type that up in the chat for me. What's an exceptional example of ways, transportation ways, where public agencies don't bear the cost of that? Any thoughts? So the correct answer to that, as I saw in the chat just now, is railroads. So railroads are a big exception to that. In the US, railroads, and that's not the case in most of the country though. But in the US, railroads are built by private firms. Obviously, they're regulated and all that, but the cost of building the railroads is borne by private, freight companies. Cost of terminals are often privately borne, parking, freight, but there might be some public agency involvement. Cost of vehicle operation are most by private entities, individual travelers, and shipping companies. Who bears the losses due to travel time? If the travel time increases significantly, who bears the cost of that? Yep, it's borne by users, the individual users, definitely. If you have losses due to travel time, individual shippers and travelers. Okay. Losses from accidents, other losses and damage, they are borne by, I think, users mostly, but then owners as well. Yep, that's right. Environmental costs, those are very interesting. Who bears the environmental costs? Right, the community is the right answer. Yep. Community is the right answer here. And this is an interesting one. So this is the slide filled up. Society in general, especially people close to a transportation facility. Now, this is interesting because what we call that is, so this environmental cost is an example of what we call that is a negative externality. Okay? And a lot of times, these types of costs get neglected because they're third-party costs, but they cause damage, but they don't cause damage to the people that are involved directly right at that moment. And so those types of costs sometimes get neglected, but they shouldn't be. Although costs are often aggregated in the economic analysis, and we're going to do that too. But the incidence of cost impacts is often critical to the final investment decision. So we have to also think about which stakeholders. So it's kind of like an equity question as well here. Is that, are we accounting for who is actually going to be bothered by this? And then there's the idea of fixed costs versus indivisible costs. And we mentioned that a little bit. Fixed cost is the idea of large front-end investment. And like, if you're going to produce a widget on a widget factory where you produce toys or whatever, right? You're going to have to build the factory first before you even produce one toy. And that's your fixed cost. So you have your large front-end investment, and they change the shape of the transportation cost function. And we're going to see that. And then there is this idea of indivisible cost. It's like the truck transport capacity only comes in truckload. You cannot get half a truckload, so you have to basically either get, and I was saying like one bulldozer versus two bulldozers if they don't rent you for half a day or hours per day. So accounting for those is also very important. So what I've done here is that starting from that idea of nominal cost being different than the real cost, if there are some underutilized resources, that developing world example where you paid the workers, but then you also provided them shelter and market and whatnot, where you recouped some of that money. So from that example on to these fixed costs and indivisible costs, what I've done is I've covered some cost concepts, like who pays as well along the way. And those things are important to keep in mind, even though the lab that we are working on currently, we are just going to aggregate all the costs. But these cost concepts need to be kept in mind as you do your analysis of projects. Joint costs. What are joint costs? Joint costs are the costs that are borne by more than one agency, right? So when the cost component is shared on an as-needed basis. So for example, think about railway and locomotive acquisition costs are needed for both passenger and freight transport. And then some portion of the pavement structure is needed for both automobile and truck travel, right? So if you think about the railroads in the US, Amtrak basically borrows the right to use those tracks from freight companies, right? There's no economic rationale, for example, especially in the case of the pavement structure, both auto and truck travel, there's no economic rationale for properly allocating joint costs. It's a matter of equity and good judgment. So it must be done, but you don't get extra benefit if you do it right. You want to do it right still, but there is no money that you make by doing the allocation correctly. Truck obviously cause much more damage to the pavements than passenger cars. So that's something that we need to keep in mind, and sometimes we might not be able to allocate that cost fairly, and that's fine. But just something to keep in mind. sunk costs, and we've talked about this a little bit, I think. The past expenditures per se are not relevant. Sunk costs are irrelevant, except to the extent that they affect future costs. So if they increase the cost of borrowing, for example, then yes, they need to be accounted for to the extent that they increase the cost of borrowing, and you just figure out how much they're exceeding the cost. And then timing. All costs must be discounted to a common point in time. I think I'm at that point home with the lab assignment and the previous set of lectures, right? So we have to account for all those. Price inflation. If it's ordinary inflation, you can ignore that. But if there is extraordinary inflation, I think I gave you the example of the fuel prices in one of the, so if you have alternatives, for example, where one of them costs way more fuel, then fuel inflation, extraordinary fuel inflation will need to be accounted for. Then there's that idea of foreign exchange. In some economies, purchases from abroad are not accurately evaluated. I recently, and you probably know this, and maybe you don't, that China uses two different currencies. One is the currency that they use for foreign exchange, and then one currency that they use for domestic exchange. I think it's the yuan and the renminbi, two different currencies that they use. So in those cases, the use of foreign exchange should be regarded as a separate resource input. Okay, and that's distinct from resources that are obtained for domestic markets and evaluated in local currency. So you might have to just keep track of those things separately. And again, that might not be super relevant in the US context, but something to keep in mind if you work in that foreign context. So there are very large economies like China that have this exact economy where they have purchases from abroad have to be evaluated using prices. The foreign exchange has to be regarded as a separate resource. Okay, so think of cost function. I'm going to stop here after this slide. Think of cost functions and supplies as supply functions. You can, if you're able to take your production function that was in the form of the rudimentary one that we saw was in the form of road rollers and laborers. If you can convert that into dollar amount and make certain assumptions about single entity or company or society bearing the cost and prevailing prices reflecting the amount of wealth tied up in the resources that we are using, we can think of production function as what we call the cost and supply function. Okay, and that's very important. You have to obviously remember the caveats that I noted in previous slides. But if you can make those assumptions and address those caveats in some ways, then you can say you can convert instead of keeping track of 5 different inputs, you can convert them all to dollar amount. And then that way, your function won't be sort of all these different inputs and amount of road produced. It will be just dollar spent and road produced. And that's what it will be if you can convert them into, so this used to be sort of multidimensional. Okay, with labor, capital, whatnot. And then that used to translate into what we call the road produced. Right? If we can make all those assumptions, so if you can make those assumptions, instead of having let me just clear all this up. I'm sorry. So this was a bunch of inputs, and they were giving you the output or road produced. right? But if you can make those assumptions, instead of having those bunch of inputs in your mix, you could have dollar spent, and you can have that relationship with road produced. Okay. So we can convert those bunch of inputs into dollar spent if we can account for all those concepts that I just talked to you about. And we will do that in general. That'll be our thing in this class, that we will be able to do that. But that doesn't mean that we can forget about all these issues that I just talked about. Okay. So I'm going to stop here now for this class. And unless there are further questions, if we leave, I don't know, maybe there's still some time to get to the farmer's market, which you can do. Yeah, if there are no further questions, feel free to drop off. And I will see you guys next week.
Thank you.